Hey guys, we're going to continue talking about vectors a little more today. We're going to talk about parallel vectors and equations of lines, okay? So, first thing we're going to go into is the definition of scalar multiples, okay? A vector W that has components W1 and W2 is a scalar multiple of vector U. Written, W equals K, which is the scalar, right? K, the scalar, times vector U. If and only if this E right here means there exists a real number K such that M times W1, W2 equals KU2. Okay? So what they're saying is they're saying W is a vector that is parallel to vector U. And we know that because there's a multiple that all it does is expand. You can think about it as its R. Its angle doesn't change. K doesn't change its angle, it changes its magnitude. So looking at one, we're going to look at W. And we're going to look at W and U, we're going to find out how they're related. So graphing W first is just going to be negative 1, 2. Okay? Negative 1, 2. So that's going to be over 1, up 2. All right, so we got that little vector going that way. Okay, and U is negative 3, 6. 3, just up there. Okay? But if you look at these actual points, okay, you can see that U is just W times a scalar 3, right? If we take W, which is our negative 1, 2, right? And we multiply it by 3, we would get negative 3, 6, which is our U. Okay? So we know that U is a scalar multiple of W, and our K equals 3. All right? And what you can take from this is how they're related. It's a multiple. Like I said, they got the same theta and a larger R. Same theta, right? Same angle, larger R. So if we go on down to 2, we're going to look at V as our vector. It's going to say calculate negative 2 times the vector V and describe this vector. So if we calculate negative 2, we're throwing our negative 2 out front of our point. It's going to give us negative 6, 8. And remember, vector, you can put the curly parentheses or you can put these. Either way, it's the same thing to me. You're not going to lose points doing both. But what you can tell from this, if you're looking at the vector, this new vector we have in our vector V, you see that the negative sign changed our direction as well as our magnitude. So when you have a negative scalar, yes, it'll change the magnitude, but it can also flip the direction, okay, the opposite direction. So that's like the same thing as adding 180. So that's the most the vector can do in direction. It can flip it and make it go the opposite direction. But if two vectors are going the opposite direction, they're still parallel. Okay, remember that. That's key. Just because they're going different directions doesn't mean they're not parallel. As long as the degree between them is 180. Okay? So they're going opposite direction and it's twice as long, right? Our scalar's 2. Now, looking at B, it says calculate. Remember, these absolute value bars are like saying norm, okay? Our absolute value bars is like finding our R. Okay, they want us to find the R. So first, though, we got to do our 5 times V. So we're going to have our 5 times V, which is 3, negative 4. Okay, that should get us 15, 20, negative 20, excuse me. Okay, now when we have to find the opposite, like now the norm value of 5v, right, we're just finding our r. So it's going to be 15 squared plus 20 squared, square root. It's going to equal 25. Okay, so in this case, they just wanted us to find the magnitude of 5 times that vector. So that's all we did. We found the norm. We found the r. We found the magnitude. 25. Change up our color. Going on down to 3. All right. The vector w begins at point 3, -7 and ends at point -4, 8. The vector u equals 6.8 times w. All right. And it's in standard position. So that just means that it's coming out of 0, right? Where does u begin and where does it end? Okay, and if it's so, the first thing we need to figure out is what our w vector is. Like, let's get our w vector into standard form. So we got, let's just do that right here. Our w is going to equal the distance between our 2 points. So our x2 minus x1, y2 minus y1. So we're going to have our -4 minus 3, 8 minus -7, same thing as plus. You're going to get -7, 15. So that's our w vector in standard form. Okay, and then it tells us that vector u is 6.8 times our w. Okay, in standard form. But we already converted to standard form, so now we can do our 6.8 times -7, 15. Okay, that should give you -47.6, 102. Okay, and so now u, because we know that w is in standard position, and we use the scalar of 6.8, what this tells us is u, it begins, it says where does it begin and end, we turned it into standard form, it begins at 0, 0, okay, and it ends at -47.6, 102, all right, so we converted our w to standard form, we used the equation they gave us with u that says 6.8 times w is u, and it gave us our standard position u vector. So that's the answer. Now let's hop into, let's give ourselves, this is going to give us some more equations to use as we go forward. So we're going to talk about parallel vectors theorem. All right, that is a non-zero vector u and v are parallel if and only if there exists a real number t that does not equal 0 such that u equals t times v. All right, so that's pretty much just saying if there's scalar multiple, if you have a vector that is a scalar multiple, it is parallel because it's either going in the same direction and has the same degree, or it's going 180 degrees in the opposite direction and it's still parallel, right? We talked about that earlier. So we have our u equals tv. Same thing as the scalar multiple, right? T is just our scalar multiple in this case. But if you can guess, they're setting us up. Oop, I wrote that in the wrong. Of course, I wrote that in the wrong one. They're setting us up to write parametric equations with vectors. Okay, so that's like saying, here's a little. Actually, we're going to hop on down to vector equation for a line. So for a vector equation for a line, okay, this might look similar. This looks kind of like something we've done before, but it's going to be x2. Think about it as x2 minus our x1, or x minus whatever the point we have is. That x initial, that x sub 0, okay, that's just the point that you have that's given, okay, right? For the line through point x naught, y naught, or x sub 0, y sub 0, that is parallel to vector v. So you're going to do x minus your x point, y minus your y point, and you're going to set it equal to t times ab, which in this case is your vector. Okay, so all these equations are going to have a point and they're going to have a vector in it. Okay, so now we are going to let's go down to parametric equations of a line. And actually, what I'm going to show you here is how we get from the vector equation to the parametric equation. But first, I want to write the parametric equation. So again, we're talking about a parametric equation for a line through point P that's parallel to vector V. All right, so we got our cool little squiggly, we got our X, we got our Y. And we have our point, our X component from our point, our Y component from our point, plus T, and it's always going to be attached to our vectors. T always has the vector attached to it. Okay, that's the big thing you got to remember. T is attached to the vector. We got our A, which is our X vector component, and B, which is our Y vector component. So the way we get from the vector line equation to the parametric equation looks something. Let's write that up right here. So we start with our xy minus our x naught minus y naught. Okay, and you don't need to have this memorized. I'm just showing you how we get from one point to the other. Okay, that's all I did was I took this and switched that up a little bit, right? I had our original x and our y point. That's what we get right there. So that's the same thing now. We can keep adjusting. We go x, y equals, take this to the other side. Okay, and from there, you already have it. Now we can just break it up into its two components. Take our x components, take our y components. This is just like what we were doing last section. Because now we have okay? See how we get that just like switching them around? So you're going to have a lot of questions. We're going to go over that a lot today about how to go from one to the other and what all these components can really tell us. So let's go into these examples. Best way to learn. Excuse me. Find the equation of the line through point 3, 4 and parallel to vector 2, 4. So vector equation. We just got to plug stuff into our equation. Vector equation. It's going to be x minus r, x point, y minus r, y point, equals t and our vector. Okay, nothing too crazy. Parametric equations. All right, same thing. We're plugging in our point. Then we're plugging in our vector, attaching it to t. Now we got to graph it. Okay, this is where things can get a little confusing. But again, we got to know what all these components can tell us. So first thing I always think about is what's the slope going to be? All right, think about it. The vector actually always tells us our slope. If you have a standard vector, it's going to always tell you your slope. Okay, so we can do our slope, our m, right, equals rise over run. So our y over our x, which is just going to be 4 over 2. Okay, or 2. So that's our slope. So we know we have a vector that goes through point 3, 4. So we go 3, we go 4, and we know it's at a slope of 2. So you can just get the next point. Right? So there we go. We found the equation through the line, or through the point 3, 4, which is right here. All right, and it's parallel to this vector, which has a slope of 2 that goes through 2, 4. So that'd be 2, 4. So this is the vector. So you got your vector and you got your line, and it's parallel. Okay. Now 4, or I guess 4 part 2, graph the equation. Okay, first thing to find out, what's our point? What's our point in all this? Our p is going to be 2, negative 3. right? Remember, those are supposed to be minus. So there we got 2, -3. Our vector is going to be -1, 3. Okay, which means our slope, our rise over run, is going to be 3 over -1, which equals -3. So first thing I like to do, we're going to graph our point. We found our slope. We have our point, 2, -3. Okay, and we know we have a slope of -3. So you can go down 3 over 1, something like this. Except hopefully it's a straighter line. Not so squiggly. Okay, that's our point P. All right, if we had the vector -1, 3, if we had the vector -1, 3, it would be this way. Oops, I actually messed that one up, didn't I? Because this point should be right there. There we go. And then our vector, like I said, -1, 3, is going to be this guy right there, parallel. Okay, so notice that vector is parallel to the line. Moving on down to 5. Find the vector equation for the line that contains the point -2, 5 and is parallel to vector v. Okay, so we're just plugging stuff into our vector equation. So take our format, our x minus our x component, which is -2, so it's same as plus. Our y minus our y component, which is 5, equals t in our vector, which is 1, -3. Okay, as easy as that. Remember, vector equation is the one that's laid out like that. Parametric equation is the ones we stack. So for 6, it's asking for a parametric. Okay, set it up like that. Find our point, which is 2, 8. 2, 8. Find our vector, which is -5, 4. Okay, so so it's the same thing as -5t plus 4t. Okay, and now we got our vector in there. And now let's just graph it. Let's graph this one for fun. Okay, if we have our point, we have our slope. You could think about it as our point is 2, 8. So let's find that one. We got 1, 2, 3, 4, 5, 6, 7, 8. Let's just say that's about right there. Okay, and we have our slope, which we get from our vector. So rise over run, 4 over -5. Okay, so let's do that by let's take our point. We're going to go down 4 over 5. So we're at 8, 7, 6, 5, 4, 1, 2, 3, 4, 5. So we got something like that. Again, hopefully you guys can draw a better line than me. I'm still not good at this on my iPad. Okay, so we know that you can use the vector to find the slope and just use your starting point and go from there. Do your rise over run, graphing stuff back in Algebra 1. That's the same thing we're doing right now. Let's hop on down to 7. Write a vector equation for the line through points -2, 5 and through point 4, -1. So first, we got to find the vector. All right, they gave us 2 points. So how do we find a vector with 2 points? We do that little subtraction. We take our x's and our y's, we subtract them. So we're going to have our v is going to equal, in standard form too, 4 minus -2. -1, I don't want to do that. -1 minus 5. Okay, that's going to equal 6, negative 6. So now we have our vector. We have a point. We could use either point, really. It does not matter what point you use because both those points are on the line we're using. So I'll draw them for both. Why not? We could have the 2, negative 5, or negative 2, 5 point. Which looks like this. Our vectors are going to always be the same. That's nice. Okay, or you could have this point, the 4, negative 1. Okay, so either or, it's same thing. Okay, the point can change. There's infinite many points on that line, right? So as long as the vector is the same, the vector tells you the slope. The point tells you that it's somewhere on that line. Okay, so you could have any point in there, really. You could find any point on that line and plug it in. Going on down to 8, they're asking us to write an equation in slope-intercept form for line 6. For the line in number 6, excuse me. So the line in number 6 is going to give us that vector negative 5, 4 and 0.28. Okay, so we have v equals negative 5, 4 and p equals 2.8. So now we're going to put this in slope-intercept form. Remember what we learned about the vector and how to find the slope? Just going to do our little rise over run. We got our 4 over negative 5, so we could just plug that in. We have 2 points, we have a slope. We could plug that into our form, solve for b. So we could have our, let's change up the color a little. We could have our 8, right? Our y point equals 4/5 times our x, which is 2 plus b. We do a little bit solving. Okay, we get here we go. Hold on. We get something that's going to end up like 48 over 5 equals b. It's an 8, excuse me. 48 over 5 equals b. Okay, if we have 48 over 5 equals b, we can write that as y equals our negative 4 over 5 x plus 48 over 5. Okay. And what we did was we just had common denominators there. That's how we got that 48. I made that a common denom. Okay. You could also do it another way, more of a standard way, which is, your y minus y1 equals mx minus x1. Okay, so we could do our y minus 8 equals negative 4 over 5 x minus 2. Then we go y minus 8 equals negative 4/5 x plus 8 over 5. But because we distribute that 4 times 5, you also get plus 40 over 5. And that's how we get our final y equals negative 4/5 x plus 48 over 5. Okay, both these are right. Same thing, 2 different ways to get them. Not so bad. Going on down to 9, it says write y equals, let's just erase that last thing. It says write y equals 3x minus 5 in vector equation form. Okay, now we're going the opposite way. So we could use any point here. So find any point, the easiest point in this situation. Okay, and we're not going to let you do this all the time, but you just plug a 0 in. Plug a 0 in for x. So if we have a point, okay, we plug 0 in for x, makes that 3, 0, minus 5, you get 0, negative 5. Okay, just plug and chug. All right, we know our slope is 3. Okay, but 3, that's the same thing as 3 over 1, right? So that's our y over x. So that can give us our vector. So we can just go the opposite way. So our vector can be 1, 3. Okay, hopefully you guys can see how I made that transition. So over here, if we write it, now we have all the pieces we need for vector equation form. Our x is 0, so we don't have to do anything. Our y plus 5, because it's negative 5, equals our t and our vector, which is 1, 3. Okay, the big thing to remember, the relationship between slope and the vector is the biggest thing. Okay, we're going to use that a lot going forward, the relationship between slope and vector. So now for 10, write this vector equation in slope-intercept form. It's not too bad. We got a point. Right, what's our point? It's going to be 3, negative 2. Our slope, we're using our vector. We're going to have 5 over negative 4. So now when we start plugging this in, we got our y plus 2 equals 5 over negative 4 x minus 3. Okay, we expand that out. You have y plus 2 equals negative 5 fourths x plus 15 over 4 minus 2 times 8 over 4. Okay, and that's going to give you y equals negative 5 fourths x plus 7 fourths. All right. Not too bad, not too bad. Now, we're going to keep going on down to 11. This is our last one. We're going to write these parametric equations in slope-intercept form. So you can do this, I like to do this the same way we did it in chapter 1, right? We can solve one equation for t, plug it into the other. So because we already have a y equals, I'd like to do that to the x. So you can say x, if I take this equation down here, that's the same thing as x minus 5 over negative 2 equals t. Okay, we can take our y equation, we can plug that right on in. All right, we solve that down. We're going to get and actually, I'm going to change that negative 4 because I want common denominators. Okay, it just makes all this addition easier. I want a common denominator. So I'm going to change this to a negative 8 over 2. And then expand this part out. 5x over negative 2 plus 25 over 2. Yeah, all I did was distribute that 5 and then separate them out. Okay, and then you have y equals negative 5 over 2x plus 17 over 2. Okay, there you have it. So, big things to take away from this section is how to find the slope. Make sure you understand what all these different forms are. Slope-intercept form, vector form, and parametric form. Understand the difference between them, understand how to get to all of them, and again, the slope is the big thing. Understand how the slope works, try to remember that stuff about standard form. All this is building off of it pretty well. So let me know if you have any questions.